In this video, I want to talk about step 2, the test statistic, and we're working through our 4 steps in a test hypothesis. And for purposes of illustration, let's say that we've come out of our first step, identifying the test, and we've said we want to test mu is equal to 100. Let's see if I can write it up here in the top, versus the alternative, mu differs. Mu is not equal to 100. Okay, and so the test statistic, that's what we've identified as our test. That's step 1. The test statistic says, all right, do we believe that? We're trying to say the mean differs from 100. We begin by assuming that it's equal to 100, and now we're going to go and collect some data. And here's the idea. When we assume the null hypothesis is true, what that means is when we take a sample, we believe, if you assume that's true, we believe that the sample data should look like this population. It should be centered at 100, because that's what we're saying. We believe the population mean is centered at 100, and so we would expect the sample information to be centered at 100 as well. And so what we're going to say is the evidence that contained in the sample is going to support either the null or the alternative. If the null is true, for instance, what would you expect for your sample mean? That's a question mark, crappy looking question mark, but it is one. If the null hypothesis is true, wouldn't we expect our sample mean to kind of be sort of close to 100? Now, because of what we know about sampling distributions and sampling variation, you probably wouldn't expect it to be exactly equal to 100, would you? I mean, if your sample mean was 99.99, I doubt you would bat an eye. You wouldn't say, oh no, the null hypothesis isn't true. If the sample mean is 100.000001, you're probably not going to freak out about it. But what if the sample mean is 7,000? What if the sample mean is 2? And really where I'm getting at here, what I'm getting at here is how far away can the sample mean be and us just consider it to be sampling variation before we start considering the possibility that maybe the null hypothesis isn't true. And in a nutshell, that's the point of what we're trying to accomplish here. Now the test statistic, this is the formula. This is the numbers part. This is the part where in a previous statistics class, I hope you didn't have to do a lot of these formulas. I'm going to show them to you here. I'm going to show you one of them at least. But I hope you didn't have to do a lot of this math. If you did, again, I'm going to apologize for that. I'm going to say I'm sorry. I don't think you needed to. We're going to approach this where we're not going to. We're going to let the computer do the math part for us. I want you to do the thinking part, but we're going to let the computer do the math part. And so here's what I'll say. Assuming H naught is true, which is how we've set all this up. We want to say the alternative is true, but we're going to start by assuming the null is true. The test statistic, the formula that we take a look at, is going to have a familiar or a known distribution. Now, a lot of you have worked with these two distributions before, Z distributions and T distributions. They're the beautiful bell-shaped curves. The T is a little bit more spread out than the Z. They're both centered at the population mean. Okay, and then we're going to do some work, and if we get to the Z distribution, it's centered at 0. But those are known distributions. There's a table out there somewhere. There's a chart where you can look up probabilities in. I'm not going to ask you to do that, but you could. You have before. Even my students, who I don't ask to do a lot of formula work in our Stat 1 class, even my students have used these tables before. They help you understand. Well, this semester we're going to run into a couple other distributions. The F distribution, the chi-squared distribution. There's others. The point is, if you assume the null is true, more arrows here, if you assume that the null hypothesis is true, we know what to expect. And so one of the test statistics that we look at is going to look like this. Okay, it's going to be a point estimate minus hypothesized value. Let's just go with symbols. Here's a good example. When you're working with a single population mean mu, which is the example I have at the top of the screen, that's the null and the alternative we'd be looking at, something like that. We've seen this before, haven't we? We've seen this would be a sampling distribution of x bar. We're going to change this. We're just going to call this, we're not going to call it mu sub x bar. We're going to call it mu naught. Now, what does that mean? What do we believe mu to be? Well, we're assuming if the null hypothesis is true that it's the value 100. And so we would be plugging the value 100 in there. We're going to get some number. We're not going to know sigma. We're going to plug in this value of the sample standard deviation here. If you're doing the math, the sample would yield a value of x bar. It would give us an estimate of the sigma here, and we would know the sample size. The only value we'd have to worry about is that mu naught, which we get from the null hypothesis. These are just numbers. The math of this part of the math right here, this part of the math right here is really the easy part. You know the tough part? Tough part is calculating x bar and calculating the standard deviation in our sample. That's where the math comes in, but we're going to let the computer do all of that. Test statistics will be found on computer output. How much time should you spend doing this? None. 0. Now, what do you do with that thing? That's a great question. Sometimes, and I'm going to use an example here, it's kind of a little different. One of my hobbies, something I've enjoyed doing in my past, I don't do it much anymore. I still have golf clubs, but I don't go golfing very much. Golfing for me now means heading over to a place called Topgolf and getting lunch, just kind of goofing around. But I used to be a golfer. I used to enjoy golfing. And one of the things I was particularly bad at was putting. And if you're not familiar with golf, you hit the ball, you eventually get to a surface called the green, which has got really short grass, and you want to putt with a flat kind of club. You want to putt the ball into a hole or a cup. And it's called putting. And it's the last stroke or two you do, maybe more than that, on a golf hole. And so there's a term in golf. There's actually a couple terms in golf that are just fun terms. One's called a mulligan. And a mulligan is a term which means do it again. Pretend that didn't exist. Just do it over. Don't count that stroke. That's a great term, one that I needed desperately when I was golfing. But another term that's a really good term, and a lot of golfers know this term, is the term gimme. It's called a gimme, G-I-M-M-E. It's a gimme. And what that means in golf terminology is that putt is so close to the hole that I know what the result's going to be. I know the conclusion of the next putt. I know you're going to make that putt. Okay? So think about a golf hole and think about a ball kind of sitting on the edge of the hole, peering over, not falling in, just sitting there, just barely missed. I know I'm going to make that next one. All I got to do is tap it and it's in. That's a gimme. That's a good example of a gimme. But what I want you to think about is a second type of gimme. Let's say you're a terrible putter, like me, for instance. Not the strength of my game. Actually, I didn't have a lot of strength in my golf game, but terrible putter. And I tell you that I've never made a putt more than 15 feet. And you're probably rolling your eyes saying, no, that's not true. It is. I'm terrible. And so in my world, in my golf world, I want you to think about another type of gimme. It's you're not going to make that putt. It's the kind of the anti-gimme, right? The gimme is I know you're going to make it. An anti-gimme would be I know you're going to miss it. And so there are certain distances. If I'm right next to the hole, I know I'm going to make that putt. If I'm more than, say, 15 feet away or so, I know I'm going to miss that next putt. Now, why am I bringing that up? That's a great question. Happens a lot to me. Ah, wait, there is a reason. Because with test statistics, there are what I'll call some automatics. There's some test statistics where I know exactly what they indicate. How do I know that? Because I know what to expect. And the distribution I'm going to go to, the distribution I'm going to talk about, is the z distribution. Sometimes, when you take a large sample, for instance, the test statistic has a distribution that should look like a z. Now, what does that mean? What that means is if I go to this distribution, if I go to the population and take a sample and calculate a value of the test statistic, it's going to give me a number in this curve up here. If I go and do it again, it's going to give me another number. And if I go and do it repeatedly, if I do it over and over and over and over and over and over and over again, if I piled those numbers up, it would look like a z distribution. Well, if it looks like a z distribution, you'd expect most of those values to fall towards the middle. You'd expect most of them, for instance, because it's a normal curve, to fall within 2 standard deviations of the mean. And because we're dealing with a z distribution, you might say between plus and minus 2. Now, there's some caveats to that. There's some tweaks to that. The plus and minus 2 is a good number to think of if you're working with 95%. Some of you might remember using a normal curve and using different reliability levels, confidence levels, alphas, to use the symbol that we're working with now. The other caveat is we're not always looking in both directions. If I was doing a not equal to test, like I've kind of specified at the top of the screen here, then 2 sides would be appropriate, but sometimes you're only interested in one direction. Maybe you're doing a greater than test. Sometimes you're only interested in the left-hand direction, which is a less than test. And so sometimes you don't want to focus your information in both directions. But the bigger point here, and we'll get into some of those specifics in the next step, the bigger point here is you know what to expect. And so if you get a test statistic that's a value like 32, If you know anything about a z-distribution, you're going to look at a value of 32 and say, no way, that's too far out. It's way out there in the tail. That's a contradiction. What does that mean? If the null is true, we're expecting to see something in this pretty little z-distribution. That's a contradiction to that. My sample data seem to contradict this distribution. I don't believe this distribution is reflecting my sample data. I'm going to reject the null hypothesis. And so I would say that would be a gimme. Here's another gimme. What if you have a test statistic of 0.14? If you ask me, what do you expect? Well, I expect a value around 0. That's pretty close to 0 there. It's a crappy box, but that's pretty close to 0. That's a gimme. That's the other type of gimme. Some of the test statistics sure make it look like the null hypothesis is okay. Gimmes. Other test statistics make it look like the null hypothesis is not okay. Anti-gimmes. Like the 32, like a -7. But here's where you run into the trouble. When I'm golfing, sometimes I have a 7-foot putt. It's not right next to the hole. It's not really far away from the hole. I don't know what the decision is going to be in that case. I don't know whether the putt's going to go in or not. I've been golfing with myself for long enough. I know it probably isn't, but I'm not sure. There's kind of a gray region there. And so we're going to need some way, some more formal way of evaluating the test statistic. What are you going to do, say, if your test statistic, let's see, 32, that's a gimme, 17 is a gimme, 5 is a gimme, 4 is a gimme. All those are unexpected. But where's your cutoff between what's expected and what's unexpected? That's an interesting thought. The test statistic is just the sample part. You've identified the test in step 1. You know, this is what we're trying to say. We want to say the alternative is true. You set it up. You're actually going to use that alternative hypothesis to figure out where to go in the software, in your computer software, to get the printout. On that printout will be this test statistic. Sometimes you'll look at that and you'll know immediately, that's a gimme. I know what to do with that one. Other times you need a little bit more help. Okay, and what we start to realize is we're going to rely less on these test statistics and the way that we evaluate them. How we do that? Come on back for step 3. So long.